Hello everyone. In this video, I will present our recent work, text prompt augmentation for zero-shot out-of-distribution detection. This work is done by me and my supervisor, Christopher. So what do we mean by OOD detection? In this work, we focus on detecting OOD data which are semantically different from the ID data. For example, if we are using the ImageNet-1k as the ID data, which are shown in the left plot, then the images from OpenImageO, ILH list, and the texture dataset can be taken as the OOD data. From the title text prompt augmentation, it implies that we're going to use vision language models, and particularly we're using CLIPc. During the inference, the input image are processed by the image encoder to obtain the image embedding. And then different semantic classes are placed into a standard prompt, such as a photo of a project, and then further processed by the text encoder to obtain the text embedding for different classes. Then we calculate the cosine similarity between the image embedding with different text embedding. Then the class with the maximum cosine similarity will be taken as the predicted class for the input image. Zero shot in our paper means that our method does not require to access in-distribution image data or OOD data. And OOD data meaning we don't have to access the image data and also the label information. The motivation behind the tag is simple. For example, if we're using a grammarly correct prompt, a photo of a china cabinet, the probability of the right class is 79. However, if we're using a grammarly incorrect prompt, such as china cabinet of a photo, then the probability of the correct class is 87. And the further similar phenomenon can be observed in another grammarly incorrect prompt. We also observe that the cosine similarity is non-uniform for the ID dataset. And this phenomenon occurs when different text augmentation are applied. For example, the left plot shows the average cosine similarity of CIFAR 100 dataset processed by VITB16. And we can see under different augmentation, the average cosine similarity are still non-uniform. Formally, our method can be defined as if we assume there are k classes in the ID dataset, and then we apply m different augmentations, then we first calculate the cosine similarity between the image embedding with the text embedding, and then apply softmax function to obtain the predictive distribution. And assuming we are using the MSP as the baseline score, then the final score would be the average of the baseline score over different augmentations. Of course, we can also replace the MSP score with the max logic score, energy score, or generalized entropy score. Here's the results for the proposed method tag. And then we can see the blue represents the baseline score, and the orange represents the performance after enhanced by the tag. And one can see that the tag in generally improve the performance in terms of both AUROC and FPR95 on two datasets, including CIFAR 100 and also ImageNet-1k. However, we found the performance improvement is less significant on ImageNet-1k. So we hypothesize that because the nerd text embedding for ImageNet-1k is not separable well for different classes. So we validate by analyzing the text embedding rank for different dataset extracted by different models. And here we can see for CFA 100 and the ImageNet-100, the text embedding usually are full rank. However, for the ImageNet-1k, we can see the rank is around 500. So it means that the text embedding for each class in ImageNet-1k is not separable well. Then we perform performance on ImageNet-100 and observe that the performance is improved when the ID dataset is ImageNet-100. Further, we combine our method with different variations of declip and the waffle clip, which are proposed to improve the zero-shot performance of CLIPc. And here is the results, and clearly our method tag can further improve the results with using different clip variations, including declip and waffle clip. To conclude, tag only uses the label information of the ID data. It doesn't require any external knowledge from the LMs or sophisticated prompt assembly. Instead, actually, it can be combined with those methods. Finally, tag can consistently achieve better results by using different score functions, including MSP, max logit energy, and gain and OOD score. And this improvement is quite significant on CFA 100 and remains on ImageNet-1k across 4 architectures and 3 baseline OOD score. Thanks for your listening.